Okay, let's start up again. Are there any questions from the first half? Guys, shh. Okay, so what does nondeterminism actually mean? It means that if we have choices that we can make any one of those choices. But what nondeterminism does, it says, oh, if I make this choice right here, and I know that it'll eventually lead me to go to a final state and accept, I will make that choice. Okay? So it's not like we can just make any choice and it simulates all possible choices. It doesn't actually do that. It makes exactly one choice. Okay? So, yeah, go ahead.
How would you do that without knowing the whole string at once?
So that's what is so magical about nondeterminism. It doesn't actually know what the string is, but it can know whether it's going to accept or not. Yeah. I love that you just went like, okay, yeah, this magical computation, it's fine. So you can never implement a non-deterministic device in the real world, right? Because you need to know the input before you've actually seen it. So why do we even care about this? Is it just because it's in the textbook and I just teach it to you and like, yep? No, it's because it allows us to accomplish these problems of concatenation, union, and star, which are about, I have this problem I want to solve, and it's composed of multiple pieces that we stick together. The model that we want to work with is the DFA model. We definitely want to work with that. But so we know how to do union with DFAs, and that's the product construction. But the problem is with concatenation and star. It's really hard to do concatenation with DFAs directly. Whereas we're computer scientists. We resort to indirection all the time. We indirectly solve this problem in another domain, and then we port it back if we need to. So that's why we made this NFA model, to make the problem solving far easier, and then we could just focus on the conversion back to make the process complete. So if you want to make a DFA for composing multiple pieces together, like some part is for example, the HTTP header, and the second part is for validating user input or something. You want to break this up into multiple pieces, but you want to use it in a deterministic finite automaton setting. So you want to break this up into concatenation because the bytes that are sent to you are just this one long string, and the first part appears here, second part appears here. And you want to be able to switch over when you need to. But you can't do that directly with DFAs. So we resort to a model of a computation which makes this far easier. Okay? So that's why we consider NFAs. And we do this in math all the time. We have this model that is really hard to solve this problem, but we have this other model that's easier. So we try to link the two models together somehow. Any other questions? Yeah.
So you were saying like it's not really applicable to the real world, but then with maybe like a header and a user information, are you able to use NFA for that?
So you can't actually build an NFA, but like in terms of an actual machine, you can draw it obviously, or specify it. But we'll be describing a process to convert it back to a DFA. So once we make it, then we can implement it in the real world. So I can't directly make it, but it does have applications in actually making something useful. I think there was one more question somewhere. Any other questions? Yeah.
So you're pretty much saying, to simplify things, if I make this into a DFA, an NFA, then that means that you can make it into a DFA, which means it's regular?
Yeah, so by doing that, we'll establish that the NFA's languages are the regular languages. Mm-hmm. Exactly. And then we'll get the closure under concatenation and star for free based off of that, once we do it. Yeah.
So the NFA will take all the possible paths, but First it will
Mm-mm.
take,
No, the NFA itself will only make one choice at every step, just like a DFA does.
but what if the selected path doesn't go into accept state?
So that if the selected path doesn't actually go to an accept state, that meant no path does, because that's what nondeterminism means. If there is a path that does go to acceptance at some point, you will choose that. That's what nondeterminism guarantees you.
What if there are multiple accept paths and we
It-
take the first one and we
It'll just pick one. We don't know necessarily which one it'll pick, but if there are multiple that lead to acceptance, it'll pick one.
so if it doesn't accept in the first path and it could be the case that it accepted it to the second path.
It'll always choose the second one in that case. If there is any choice that leads to acceptance, it'll make that choice, whatever that choice that is. So it's a magical choice selector.
There is no parallelism. It's just
There's no parallelism with simulating it in an NFA setting. If I want to simulate it deterministically, then I have to do parallelism. Yes. Because I don't know which choice is going to work. Did you have a question?
It was that.
Okay. Other questions? Okay, so let's actually do this formally. So what we'll show is that we can convert. So this is definitely a formal description of a theorem. Can convert any NFA to an equivalent DFA. And by equivalent here, I mean they have the same language. And if we can show this, then we're all set in getting the closure results that we wanted before. Okay. So how in the world are we going to prove this? Well, let's see. So if I can give you an algorithm, say, I present to you an NFA, and the algorithm makes the DFA, is that all we need? So if I give you an algorithm to actually convert the NFA to a DFA, is this all we need? Yeah, that's all we need. Cool. So let's actually consider an NFA. So let M be an NFA with Q sigma delta Q0F. So states Q, input alphabet transition, start state, final states. So no problem. Here we have an NFA right here. I want to actually make a DFA out of this thing. Well, let's see. Well, at each point right here, in our simulation here, could we possibly be in no states at a given point of the NFA? Is there a place where we can get stuck in our computation and not be able to proceed any further? Yeah, so like the Q0 reading a 1 example, there's nowhere to go. So for some places, I could have a choice that is bad and gives me 0 states out of it. Well, what about the other case? Could I go to all of the states possibly? So I can be in all states via some choices that I made. Could I possibly do that? Maybe not with this example, but in principle I could. Could I go to any subset of states, possibly? Well, let's see. Well, at this point right here, the one before we read anything, what is the set of states that I can reach before I've read anything? What is the set of states I can go to without reading a single anything? Just Q0 and Q1. So those are the states I can reach right here. What about right here? After we've read the 1, What is the set of states that I can reach after reading a 1? Just Q2. Remember? So this is just a set of states. So the states that I can reach is just Q2 only. And at the end, we again have Q0, Q1. Oh, wait a second. So what does this tell us right here? It tells us, well, if you're in either Q0 or Q1 and you read a 1, the only state you could ever eventually get to is Q2. That's the only place you can go. Well, from Q2 reading a 0, you can go to these two states, Q0, Q1. Do you think that has some kind of relation on how we should make a deterministic machine? What if we made the sets of states right here, the Q0, Q1, and Q2, what if we made those as states? What if we did something like this? Let's just keep it up here, I guess. What if we did Q0, Q1 as a state itself? And we made Q2 a state itself. Well, how would I relate these two states together based on our computation that we did? Yeah, so reading a 1 from the top one would come down here. And reading a 0 from the Q2 state will go back up here. So does the name of the state in the DFA matter? The actual name of the state? No. But do you think it serves a purpose by labeling it like this? Yeah. How did we know to accept at the end? Oh, we had a path that led to Q1. Well, we had another path that led to Q0, and Q0 is not final. Why did we accept here? Well, is there some path that led to acceptance? Yeah. Well, in this, just look at the states now, the Q0, Q1, Q2 states up on the right. Which of those two states should be final? So remember, the name of the state says these are the states you could reach at this point. Well, if I can reach Q2, does that mean I should accept? No, it doesn't mean I should accept. So Q2 should not be final. What about Q0, Q1? Should that be final? Yeah, because at least one of the states is a final state from the NFA. Because Q1 was final, that means that this whole state must be final. Okay? What state of these two should be the start state? Q0, Q1. Because Q0 was the start state before, so Q0 really should be the start state, but we're going to actually have to do something about this epsilon business. So in fact, Q0, Q1 is the start state here. Is this a complete DFA? No, what is missing? Well, the 0 from the Q0, Q1 thing. And so what would it be in that case? Well, what would a Q0, Q1 go? So from Q0 only, just ignore the epsilon transition, just Q0, where can I go on input 0? Just go to Q2. So I'm going to maintain a list of what we can reach so far. So we can reach Q2, that's fine. From Q1, where can I reach from input 0? Let's see. Well, I can reach Q1. Oh, sorry, I'm not paying attention. So I can only reach Q2. Have we made that state already? Yeah, so in fact, we can just put a 0 on this transition and we're done with that part. Are we done making a full DFA now? No. So what else do we need to do? Yeah, what does the Q2 transition do on 1? It stays there. Because why? Well, Q2 can only reach itself on input 1. Can Q2 go anywhere else on epsilon transitions? No. So in fact, we're stuck at just Q2. So in fact, this is a full DFA once we put that final state on. So the NFA on the left and the DFA on the right have the same language because we're simulating the NFA in all possible ways at the same time. Because we're only concerned about at least one path leading to acceptance. Okay, well, how many subsets of 3 states are there? If I have 3 states, how many subsets are possible? 8. I only have 2 states here. What happened to the other 6? They're not possible, right? So from the DFA here, we considered all possible things we could do, and we basically closed the branches, so to speak. So there's nothing else we need to do for the DFA, so they're not reachable. So the other 6 configurations, the other 6 subsets, we can't actually access those subsets. But could we possibly access all of them in the general case? Not just this example, but could we do all possible subsets possibly? Okay, well, let's actually consider that when we do our conversion in the general case. So let's actually construct a DFA, D for Dougherty, obviously, Q prime, sigma, so the same input alphabet, different transition, different start state, different final states. Well, what are the states of the DFA going to be here? So I don't know whether some of the subsets are not going to work. So we might as well just put all of them in. Even if they don't work, we might as well put them in. Yeah.
The final state or initial state of both the NFA and DFA would be same?
Yeah, I'll address that eventually. You have a good point. Wouldn't the start state of the DFA over here be the same? But remember, the DFA doesn't have epsilon transitions. So we need to be able to include anywhere you could reach in the NFA via epsilon transitions because the DFA doesn't have them. So it's like you could have started in any of the states you could have reached via epsilon transitions. So we'll handle that business in a bit, but we're going to ignore it for now, conveniently. Okay, well, I don't know if some of the subsets won't work. So how do I say, well, any of the subsets of states could work? Someone said it. Power set. What if we just said the power set of the NFA states? Would that work? Well, that's kind of what we're doing up here. We're just having all the subsets of the NFA as states in the DFA. So the Q0, Q1 subset, that's a state in the DFA. The Q2 subset, that's a state in the DFA. Do you think the DFA will have a state labeled empty set? Is the empty set a subset of the state set? Yeah, it's a subset of everything. So, yeah, so all possible subsets that you could reach will be in here. What about the start state? So, conveniently, we're going to ignore the epsilon transitions for now. Well, the states in the DFA are what in the NFA? The states in the DFA are modeling what in the NFA? Not quite. Was there? Yeah. So each of the DFA states is corresponding to a set of states in the NFA? Well, the DFA state, the Q0 prime here, the state in the DFA, what is it going to correspond to in the NFA? A what of states? A set of states. So we better write down a set of states. Well, what should be in this set? Or what should definitely be in this set? The start state of the NFA, which is Q0 in this case. You notice I left a little room between the equals and the curly bracket. I'm going to address that. Because we have these epsilon transitions, we'll deal with that later. Okay, well, let's see. Let's do final states. Because the transition function, like always, is the hardest thing. So let's leave the hardest thing to last. The final states, remember, is a set of states. The final states are always a set of states. So that's always true. Well, how did we, from the DFA up here, the Q0, Q1 state, how did we know that was final? How did we mark that final before? Yeah, because one of the elements inside of it was originally a final state in the NFA, namely Q1. I didn't care about Q0. Q1 was a final state before. So you can think of this as saying it's all the subsets such that they have non-empty intersection with the final states. So in other words, all the states in the DFA, if they have a Q1 anywhere inside of it, they are final. Because I could reach Q1, that means that it should be a final state in the DFA. Okay, so what do we do here? So it's all the subsets X of the set of states in the NFA. So let's be clear here. The Q right here in the set is the set of states in the NFA. The reason I'm doing this will be clear in a second. But it's all subsets such that X has non-empty intersection with the final states of the NFA. So, what in the world did I just write? It's all subsets which correspond to states in the DFA, remember? DFA states are sets of states in the NFA. Again, if you repeat it to yourself 100 times, you're almost halfway there.
Can you clarify if that's F prime and if that is F prime too?
Oh, oops, you're right. F prime. My bad. F prime on the left means the final states in the DFA. The F on the inside, I do mean the NFA's final states. So what do we mean here? Is all the states in the DFA where one of the elements in that set was originally a final state in the NFA. And that's all we mean from that. So that means exactly what we wanted up here. There was one member, at least, of Q0, Q1, which was a final state before. That's all we mean. Any questions about those three parts? Okay, let's do transition function. In general, what does a transition function take as input? What two things? State and input symbol. What about epsilon? What are we making? A DFA. Should we do epsilon here? Good. So you're paying attention. So delta prime. So this is for the DFA. What are states in the DFA modeling in the NFA? Sets of states. So I'm actually going to use X here. So X, comma A. So if we have a particular subset X and the symbol A, we want to know where we can go in the NFA to make it correspond to a state in the DFA. Well, let's see. How did we know at the beginning, so on the left of this vertical bar, how did we know to go to Q0, Q1? How did that become the start state? In general.
Is it the epsilon?
Yeah, ignore the epsilon here.
Q0 is the start.
Well, Q0 is the start state, but we have another state that we could have reached. Ignore the fact that it's an epsilon transition for now. There's another state we can reach. What did we do with these two things together? We had a set which had Q0 in it. We had another set which had Q1 in it. What did we do to those two sets? We union them together. What about the one for after reading 1? So the first one was empty set, and the other one was Q2. What did we do to those two? We had empty set here, and set containing Q2 over here. What did we do to those two? Union. What is anything union the empty set? The original set, right. So in fact, what we're doing here is we're looking at each of the elements inside this subset right here. So let's look at this subset right here. So we're looking at, hey, what does Q0 do on some symbol? Figure out where it goes, and then maintain a set of where we can go. Then we transition over to Q1. We ask, where can you go on the same symbol? And then union the results together. What if we had 10,000 states in this set? What would we do? We would look at each of them in turn. This state goes certain places, this state, and then all other 9,997 other states. And then we would just union them all together because we just need to maintain where we could go, okay? So in fact, all we need to do is just union all the results together. So what we're going to do is, well, X right here is a set of states, okay? So then, for that reason, we need to look at the union of every, let's do a different notation to make it easier to read. Let's look at a state Y in this set X. So each Y here is going to be each of the states in turn, figure out where to go for each individual Y, union the results together. Well, how can I figure out, I'm scrolling up for a reason, how can I figure out where Y, the state Y in the NFA went on the symbol A? How can I figure out where it went? Look at what transition function? The NFA's one, which is called what in this case? Yeah, it's delta of, so delta is the NFA one. So here it would be YA. Excellent. So all we're doing is we're just simulating the NFA deterministically. We're just looking at all possibilities that you could reach in one transition, make a set out of all those states, and then make the transition in the DFA go to that subset of states. Are we done? Again, you can tell by my tone it isn't. What are we forgetting? The what kind of transition? Epsilon. And in fact, we've left it out in a few places. First off, the new start state here doesn't incorporate that because we said that right here, the start state is the set containing just a single state, whereas before, we had the start state containing two things. And we left it out of the transition function where we just said we just look at the states you can reach via the character read, but ignored the epsilon transitions afterward. So what are we going to do? Well, what we should do is figure out where we can reach via only epsilon transitions. So look at the example right here on the left. Where can I reach from Q2 via only epsilon transitions or not applying any at all? Well, what state can I definitely reach from Q2 without doing anything? Yeah, Q2 only. Can I reach anywhere else? No. So what about, say, just from Q0 only? Where can I reach from epsilon transitions or not doing anything at all? Q0 or Q1. So it's what we term this as to mean is we're trying to take a closure of something. We're trying to go as far as we possibly can, spread our wings as far as we can go, while doing some action, which in this case is only doing epsilon transitions. We don't want to actually read. So that's what we're going to define right now is the epsilon closure of a set of states, states X is the smallest subset Y such that the following occurs. Well, no matter what happens, if we have a set of states and there's no epsilon transitions we could apply from only those states, well, we better just be able to get to these states only, right? We want to include the states that we're already in. So we better have that X is a subset of Y. So Y includes everything we could already reach. So the epsilon closure of a set of states always includes the original set itself. But it might include other things. A small subset Y such that if there is a transition, I should say epsilon transition, where we have some state Q having an epsilon transition to state Q prime, where Q is in X, Q prime is in, is not in X, then Q prime is in Y. Yeah, I think that's fine. Making this up as we go. Kidding. So what does this mean? This says that we have a set of states right here. And let's just say that an epsilon transition is poking its head outside of this set. Well, could we reach the state that's immediately outside of that set? Could we reach it by only epsilon transitions? So let's just say we have this situation where we have a bunch of states in here, and we have one state on the right here that has an epsilon transition. So this set is X. That we have this epsilon transition that goes to this state outside of the set. The epsilon closure says we're going to include that state in the set Y. So we're building up where we can reach from X via only epsilon transitions. Okay. Could we have a situation where I have a state out here that has an epsilon transition on the way in? Should I include the outer state here? No, because the state from the tail of the transition wasn't originally in our set, so we do not necessarily can reach the outer state. We can reach the inner one, but not necessarily the outer one. But if we have a transition that goes outside, we can definitely reach the other one. And we will denote this by the E of X. So it's the E on the front means epsilon closure of X. So in the example we had before, the epsilon closure of just Q2 is just Q2. The epsilon closure of just Q0 is the set Q0, Q1, because we just include everything else we can reach and keep building until we can't anymore. Any questions about this? Okay, so we're almost done, I promise. No jokes. So what about our construction of our DFA? What do we need to amend here? Let's start with the start state. What do we need to amend to that? Yeah, epsilon closure, because if I start in the start state of the NFA, I might have epsilon transitions poking out, and I might be able to take those. So we should put epsilon closure on the front, because we just start in Q0 and figure out where else we can reach. Okay, well, the final states are okay because that's just a determination of whether a state is final or not. So the only thing we need to really change then is the transition function. Well, the way that we did it is we applied a transition, a character reading transition, and then we asked, can we reach anywhere else via epsilon transitions? So what we need to do then is put a E on the front and wrap this whole thing on the inside. So all we're asking is figure out everything you can reach via a single character transition, and then once you have that set of states, figure out anywhere else you could reach. Any questions about that? We're going to do an example, I promise. Yeah.
Shouldn't we also do epsilon closure on X?
No, I don't, because it's just the only thing that we needed to know from the NFA's perspective is whether one of these states is final. So I only need to know what the states actually are. I don't need to figure out what things I can reach via epsilon transition.
But in the delta
In the what part?
delta prime.
Yeah, delta prime, yeah.
So we are only taking the states X, but shouldn't we take the epsilon closure of X?
Oh, okay, so what you're asking essentially, so I'm convoluting what you're going to say. Don't you love when a speaker does that? What happens is, what we're doing is we're applying the transition, then doing the epsilon stuff. Whereas what you're saying is, do the epsilon stuff, then apply the transition. Okay, is that what you're saying? So these two differences are, they pretty much are the same, essentially. But you can actually create an example where doing the second one is not the right way and the first one is correct. But to give you an idea of why that's wrong, the reason why we do it in this order is because of the start state. Because we do epsilon there, so we figure out where we can go from the start state on epsilon. But then if we did epsilon first and then the transition, then once we do the epsilon closure of the start state, we're already done. We can't go any further anyway. So the epsilon step wouldn't actually do anything for us. So we need to do it in the character then epsilon transition order, not the other way around, because of the start state. But I understand that it seems like you can do one over the other, but you can actually create an example where the other order is not the right way.
And what if we apply to the both epsilon closure on the first part and then second order?
Oh, so you mean like the X down here? So he's asking, why don't you apply epsilon closure down here? And the reason is, if you apply epsilon closure right here, it's not the right order because you're doing epsilon closure first, but it doesn't actually really matter. So I guess you could do it, but there's no real purpose because once we go to that state, we've already applied epsilon closure to get to there anyway. So in like the previous transition or at the start, we applied Epsilon Closure to begin with. So applying it again won't do anything.
I'm saying we have set of states X and we apply Epsilon Closure, then consume a connector, and then apply Epsilon Closure again.
Okay, so what I think you're saying is this. Apply, yeah. So there's actually no difference here. So it won't actually make a difference. So this is asking, apply a transition, figure out where you can go here. Transition, figure out where you can go here, etc. And then once I have this big tree of where I can go, figure out where else I can go. But you can see that I've already expanded each part as far as I can go anyway. So it actually won't make a difference here. I do need the outer one, but the inner one, I guess, is redundant. It's not necessary. I want to get into an example unless there are other questions. Okay, let's do an example because I'm sure we're all dying for one. All right, so let's do this one. Oh, and by the way, what does this prove about closure under concatenation and star?
It's also regular language.
Yeah, regular languages are closed under concat and star. And there's actually a name for this construction. It's called the Powerset Construction. I should have mentioned that earlier. And you may wonder why it's called Powerset. Because we're taking the power set of the set of states. Like the product construction did the Cartesian product, we're doing power set. Yeah.
This also shows that NFA is closed under regular language. Correct.
That they recognize the regular languages.
Yeah.
So DFAs and NFAs are that they recognize the same languages.
Yeah,
Yeah,
they're equivalent now.
yeah, they are equivalent power. Yep.
Using Powerset Construction as the first one that
I can't hear you.
Powerset Construction first one that parentheses.
Including the e's, and not the last one because it's not actually how CSE355 does it. But as this, yes.
Okay, those are the Powerset.
Yeah, that's the whole construction. Suppose that my my NFA has 10,000 states. Okay, how many states will my DFA have? How many? If I have n elements in a set, how big is the power set? To the n. So how many states would my DFA have? 2 to the power 10,000. Do you think I want to make a DFA that big? Hell no. Okay? So I'm going to actually show you a much better way to make our DFAs so that we don't make any redundant states or inaccessible states, I guess. So let's do this example. B back here. Let's make this more interesting. Okay. Yeah, I think that's okay. I'm trying to visualize how many states we'll actually need, and I don't think it's that many. If it's too many, we'll run out of time. All right. So we need to be able to make a DFA. So this is the NFA. We want to make a DFA for the same language. So how do I make the start state of the DFA here? Epsilon closure of the start state, which is what in this case? Q0, Q1, because I can't get anywhere else with epsilon closure. So I'm going to make the set Q0, Q1 be a state, the start state. Can I zoom out? Yes, I can. Cool. So let's just say the characters in the alphabet are A and B. So where can I go from Q0, Q1? Let's make it simple. On B. Where can I go on B? Nowhere. Oh. What's that state going to be? Ooh, empty set. Anyone else that excited about the empty set? I'm excited about the empty set. So, I mean, it's just a state name. What should the empty set state do on A and B? Just loop, right? And should it be final? No, it shouldn't be final. Cool. So one of the only joys in my life in teaching this class is when you do the transition here and completely close it off and not have to think about it anymore. So the B path is done. Are we done making the DFA? No. So what else do we need to do? We need to do the A transition. Well, where can I go from Q0 on A? Nowhere. Cool. What about Q1? Where can we go on A? Q2 and Q3. So that's the set of states I'm going to write down so far. Can I get anywhere else from Q2 and Q3 via epsilon transitions? No, I can't get anywhere. Cool. So that's the set of states that I have now. Okay, so what about, so now we got to deal with the 2-3 state right here. Where can we go on input A from 2 and 3? Where can Q2 go on A? Nowhere. Q3 on A?
No.
Nowhere. Oh, what state is that? Empty set. Isn't it nice when the paths just come back to states you already made? What about the B transition? Where does Q2 go on B? Q2 and? Q0. We'll deal with that in a second. Let's see. Can Q3 go anywhere on B? No. Here's an important question. What is the epsilon closure of 0 and 2? Where else can I go from those two states only on epsilon? Q1 from Q0 and 3 from 2. So I better include those states as well. Okay, great. What about on B? For this monstrous state. What about on B? Where does it go? Well, this set includes 2 and 3. So doesn't it go to all states? Ah, so that's easy. So this loops on B because 2 and 3 get to all the states, so I don't really care about what 0 and 1 do because I'm just unioning everything. But what about on A? Well, where does 0 go on A? Nowhere. Great. 1 on A. So 2 and 3. Oops. 2 and 3 so far. Where else can we go? What about Q2 on A? Where does it go? Nowhere. 3 on A. Where does it go? Nowhere. So what is the epsilon closure of 2 and 3? Can I get anywhere else from 2 and 3 to anywhere else? No. Oh, do we have a state already called 2, 3? Ah, yes. So in fact, we can close off all paths like this. Is the DFA done? No, what is left? Final stage. Which ones are the final states? Anything containing Q3. So 0 and 1, definitely not. Empty set, should that one be final? No. Does it contain Q3? No. Good. So 2 and 3 definitely is. And certainly the one that has all states. And Geico and yeah, AAA. Anyway, cool. So in fact, we can make, so how many states could I have made if there are 4 states in the NFA? 2 to the 4, which is 16. The other 12 states are completely unreachable. Isn't this a lot easier, building the states as you go? Cool, I'll see you next time.